Okay, good afternoon, everyone. I'm Balakrishnan Vishwanathan. So I'm a postdoc with Professor Subhashish Ghosh. So my area of research is broadly in quantum optics. So far, I've been working on exploring nonlinear optical schemes at the single photon level for quantum logical operations. And off late, my interest has shifted to quantum imaging and studying entanglement in photonic systems. So the motivation behind these lectures is that we have a large optics and quantum information group, so where people have interest in different aspects of quantum information science. So the goal was if we can have a structured discussion on certain aspects of quantum optics so that we can try to have people working on quantum information science get interested in some of the quantum technology protocols on a photonic platform. So that's the motivation behind these lectures. So, of course, this is not going to be a traditional course in quantum optics in a sense where we won't be starting with the quantization of radiation fields. So instead, we'll focus on certain aspects of quantum optics, particularly optical coherence in classical optics. What is the notion of coherence? What interference means in optics? The notion of spatial and temporal coherence. And then we'll try to discuss how the concept of uh, angular spectrum of the pump enters the analysis. And then we will slowly branch off to quantum optics, where we'll discuss correlations, what correlations mean in quantum optics, like the concept of photon bunching, anti-bunching, so on and so forth. And once we discuss all these things, we will gradually move over to optical interferometry. So we will discuss Hongu-Mandel interferometer. We will discuss Mach-Zehnder interferometer. We will discuss the Zhu-Wang-Mandel interferometer. We will do the analysis first in the single mode picture. And later, we will move to multimode treatment, because that is multimode treatment is more realistic and it's much closer to the experiments. Following that, we will then study the phenomenon of spontaneous parametric down conversion. Like that is the workhorse of every quantum optics experimentalist to produce entangled photons. So we will try to understand the theory of spontaneous parametric down conversion in reasonable detail, and then try to appreciate the notion of interference in the quantum regime, what spatial and temporal coherence mean in quantum optics too. We will first discuss all these concepts in classical optics and then move over to quantum optics. So finally, we will try to, if time permits, we will try to discuss the concept of lasers, the physics of lasers. Okay, maybe a semi-classical treatment, because the quantum treatment of laser would be more involved, and for that we may have to discuss certain ideas from open quantum systems. Of course, in this semester, we are leaving out a major chunk of quantum optics. Basically, we won't have time to discuss light-matter interaction, which is one of the pillars of quantum optics and which has been one of the most active areas of research over the last 30 years. And we will not be discussing cavity QED, and we may not have time to discuss open quantum systems like the spin systems, dissipative harmonic oscillators, so on and so forth. So maybe next semester we can try to discuss some of these ideas. But for the next 3 months, the focus will be entirely on optical coherence and in classical and quantum optics and interferometry. Okay. So, okay, so today, we will first intuitively try to understand the concept of coherence. Okay, so what coherence means. So today's lecture discussion will be mostly intuitive, where we'll try to understand physically what coherence means, and we'll try to derive some very simple formulas that most of you might have seen in your high school or in your undergraduate physics. But those ideas are very important. And we'll also try to get a feeling for some of the numbers, like what the coherence length and coherence time of various optical sources are. So one of the goals as this course progresses would be to also get a feeling for the numbers which experimentalists use. So along with the theoretical treatment, we'll also try to put some values for various parameters and try to appreciate the orders of magnitude, because that's very important if you want to appreciate the research literature. So what is coherence? So coherence simply means that how the amplitude and phase of an optical field remain correlated between two different space-time points. Okay. In other words, coherence means, is the amplitude and phase of an optical field predictable? Or does the optical field still retain its sinusoidal form? That's what is meant by coherence. Okay. Now, in an ideal case, we always assume that a wave is harmonic forever. Okay? Like we say, we always assume that the wave is infinitely long, and at any given instant of time, you can always precisely measure the amplitude and phase, and the phase and amplitude will remain predictable at arbitrary instants of time and space. But that is not the case in any real optical field. In any real optical field, you won't be able to predict the amplitude and phase at arbitrary locations and at arbitrary instants of time. Okay? They remain correlated only for a finite duration and for over a finite distance. Okay? And that finite duration of time for which the amplitude and the phase of an optical field remain predictable is called the coherence time. Okay? And that we denote it by the symbol tau. Now, the distance over which the amplitude and field remain predictable or stay correlated. So when I say being predictable, it means they are correlated. In a sense, the values they don't take random values. That's what I mean. Okay, and that distance is called coherence length. Or in a much simpler language, you can always think of the coherence time, as a time over which the optical field maintains its sinusoidal character or its harmonic character. Likewise, the coherence length, is the length over which the field retains its harmonic nature. So for example, so basically, if you have a wave packet or a field like this, then typically this will be a coherence length, because you can see that over this distance, the amplitude and phase are predictable. And if you see that at the two corners, the phase changes, there is a break in the phase. So which means beyond this point, you lose the coherence. Okay? And the time over which this behavior is observed is called the coherence time. Okay, that's one thing. So there are two types of coherence in optics. One is called temporal coherence. The other one is called spatial coherence. And as these names suggest, temporal coherence refers to the correlation between the phases and amplitudes of a field at two different instants of time. That's why it's called temporal. Okay, and spatial coherence simply means the same behavior, the correlations between the amplitude and phase at two different spatial coordinates. That's why it's called spatial coherence. Now, temporal coherence is related to the finite bandwidth of the optical field. Okay, and the spatial coherence is related to, we will see this point in a few minutes, but spatial coherence is related to the finite size of the source, the source that produces the field. Okay. Now, in high school, whenever we studied Young's double slit experiment, we always assume that the source is just a point object. We always assumed a point source, but that's not the case in the real world. So any optical source, any source of an optical field has a finite size. Okay, and that finite size does influence the nature of coherence of the field that it produces. Okay, and likewise, no pulse that you observe or that you generate or you observe in a real world is infinitely long. Okay, every pulse has a finite duration. Every wave packet has a finite bandwidth. It has a finite spectral width. Okay, and it is this finite bandwidth, and this finite bandwidth arises out of the temporal coherence. Okay.
What do you mean by bandwidth?
Okay. Assume that this is some pulse. Okay, this is the peak. So that is, I'm just plotting this as a function of lambda. Okay, you try to see, you take all the modes, all the spectral components of your pulse into account, and this is where you observe the peak. Okay. Yeah, the intensity as a function of lambda. Exactly. It's just a spread around the central frequency wavelength or the mean wavelength, whatever you want to call it. Okay. We call this lambda naught. So this is the width. So all the energy of your pulse, pretty much most of the energy contained in the pulse, will be contained in this region. Okay. So that's what you mean by the bandwidth, or you call it the spectral width, whatever you want to call it. The same thing if you consider it in the time domain, you plot the pulse, the intensity as a function of time, that bandwidth becomes the duration of the pulse. Okay, how long the pulse persists before it dies off or it decays. Of course, the coherence length and coherence time are related by the straightforward formula. C is the speed of light. So this is going to be in vacuum. Of course, if you were to study this in an optical medium, then you have to consider the appropriate speed of light, because the speed of light changes when it propagates through a material medium. But the discussion today will just consider the propagation of waves and optical fields in vacuum, in air, in free space. Okay, so this is how the coherence length and coherence time are related.
So if in that way, coherence length is it's finite. So after some time, coherence time will also be finite.
Yeah, exactly.
So after some time, this wave will change in a way that it's not harmonic in any.
No, it's what. So
what will it look like?
So no, the way it happens is, you see, a source has many atoms. Okay, now each atom emits. So the origin of the coherence length and coherence time is the following: a source has many emitters, many atoms. So each atom emits randomly. They are statistically independent. The emission by each atom in the source is in no way correlated with the emission from its neighboring atoms. Okay, so which means whatever field that you observe in nature, say from a mercury lamp or whatever, be it from an argon lamp, whatever, sodium vapor lamp, is basically a superposition of the field or the wave generated by each and every atom. Okay, so let us say that this is one such wave pulse generated by one of the atoms. Now the second atom will, the wave generated by the second atom will be something like this. Okay, and you see that there's a phase break. Okay, now if I call this point A and call this point B, there is no way the phase at A will have any correlation with the phase at B. Okay, so if you want to do any kind of interference, you will have to do that over this length scale and time scale. So what do I mean by this? This coherence length gives you, it provides you with an upper bound on the path difference, on the difference in the path length between the two arms of the interferometer. So the way you do interference is, a simple Michelson interferometer is, you have a source, you have a beam splitter, and then you put some mirror here, and this is your detector, correct? Now this is one arm, this is another arm. Okay, to observe interference there should be a difference in the path lengths. So L2 minus L1 should have some finite value, right? So let us call that delta L, and this coherence length provides you an upper bound. So you get interference with the best contrast when delta L is much less than, but the upper limit, the fringes will begin to disappear, or the fringes will begin to become poorer and poorer when you reach this limit. The moment the difference in the path length gets larger than L sub c, the coherence length, there won't be any interference. Okay, that's one thing. So that's the importance of coherence length. And again, if you add the waves generated by each and every atom from the source, they will not be coherent. All the waves together, the superposed field will not be coherent with each other. Okay, so they will only, you can only measure coherence for each wave packet, because in general there won't be any phase dependence, there won't be any correlation between the waves generated by each atom, by all the atoms, because they emit randomly. The process of emission by the atoms in a source are statistically independent. Okay, so that's the notion of spatial and temporal coherence here. So any question, comment, clarification? Yeah, please feel free to stop me if something is not clear. Okay, so now the bandwidth of the medium. Yeah, please, go ahead.
How would you quantify LC? I can understand it, but given a wave, how would you?
So you mean in a lab? How do I measure, get a feel in the numbers? That's what you're asking?
Mathematically, maybe tau C or an LC. How do you actually get an estimate of this?
So what you do is, the way you can get an estimate of L sub c, in the lab we first measure L sub c, and then from that we measure, we infer the coherence time tau sub c. So what do? You just build this setup. This is called Michelson interferometer.
At the point where the fringes start disappearing, that it will give you the
exactly. Spot on. Yes, that's what you do.
And mathematically, how would you, if you given a wave, how would you estimate?
Oh, that's what, it's just a number. So L sub c is just a number.
Theoretically, like if I give you a wave function which evolves over time.
Oh no, L sub c is something that you have to determine. This is not something that you, the value of L sub c is not something that you can deduce from some first principles calculation. So
I mean, it has to correspond to some theoretical estimate.
No. So that L sub c is, so you mean, no, L sub c, the coherence time and coherence length for each source is determined experimentally.
Yeah.
So what he's asking, I guess, is that if you look at some optical field, it has some wave. Now, by looking at the field, can one get an estimate of L sub c? So he says that, I look at the largest length where this will behave almost like a sinusoidal.
Yes. So intuitively, we can see from the picture that you draw that that is LC. But how do we estimate it mathematically, actually? From that pulse, it's clear. So the only way, if you want to estimate it mathematically, then which means if you can maybe the decomposition and then where it peaks, that is the no. That will give you estimate of Fourier decomposition. Will give you. No. So this, if you want to really observe it, if you're given an optical field, then you will simply have to plot, or rather observe its evolution as a function of z, assuming that it propagates along the z direction for simplicity. Okay, and then you will have to really see how long you see a correlation in the amplitude and phase of that wave packet or that pulse. The region where it breaks, there's a breakage of phase. That's when you lose the coherence.
Is there anything like correlation function, like correlation length?
No. Of course, correlation functions come naturally. That's what we'll be doing next, or the next few lectures, not today. But you because the sources, you are right, the correlation functions are necessary to study interference more rigorously. But the concept of L sub c and tau c, these are parameters.
Purely like
the values are determined from experiments. So this is not something, the notion of this L sub c and tau sub c as a concept you can introduce on a piece of paper, but the values are determined experimentally. Right. So to your question, Prem, so the only ways you will have to, if you have a real optical field, you will have to plot its evolution, its propagation basically, and see how long, over what distance you see a correlation in the amplitude and phase of that optical field. But in experiment, what you do is you build this Michelson interferometer. So initially you set L1 and L2 to be the same. Basically the mirror, this is a beam splitter, by the way. Okay. Then what you do is you mount one of the mirrors on a moving stage and then try to slowly move this mirror. So each time you move the mirror, it's one arm will have a different path length compared to the other. Okay, you keep playing with this and keep observing the contrast of your interference fringes. Okay, now if the wave is coherent, if the optical field is carries if it stays coherent, then your interference fringes should be very clear. Should be able to distinctly distinguish between the bright and the dark fringes. Okay, now the moment the contrast vanishes or becomes poorer, then which means you have shot past the coherence length. So basically the coherence length is the largest difference in the path length that you can have and still observe a good quality interference. That's how you measure the coherence length. Okay.
What we need to understand that why making this difference between L1 and L2. First of all, why the coherence is disappeared. That's the reason we have to find out. And then only we can contrast with this. What's the reason that after that it just disappears? What is the physical principle? What is the physics principle?
So the physical principle is beyond that coherence length. When you cross L sub c, the optical field loses its sinusoidal character. So which means you won't be able to so no longer will you be able to represent the optical field as a simple harmonic function. So which means the amplitude and the phase beyond LC will not be predictable. They become random. So until this length, you can see that from the simple sketch, the amplitude and the phase are predictable at all points over this distance. Okay, when you go beyond this, then they no longer remain predictable.
Basically, they lose some sort of periodicity.
Yeah, they lose periodicity. In a sense, for interference, to observe interference, you need the predictability of the amplitude and phase will have to be preserved to observe interference. Yes. So which means if you know, so for example, over this distance, if you know the phase at this point, then you can predict what will be the phase at some other point here. Likewise here. Okay, and likewise for the amplitude. Okay, and you lose that predictability beyond the coherence length. Phase will be random, the amplitude will be random. So which means beyond that coherence length, the fields will not interfere. You can't observe interference. So if you make this, so in this simple setup, if you make delta L larger than L sub C, so all you will see is some fuzzy distribution of intensities. You won't see the interference fringes. So you won't be able to see the bright, distinctly you won't be able to see the bright and the dark fringes. Yeah.
Suppose we have a wave packet. It evolves with time. So like, is it possible that the coherence length also changes with time?
No. The coherence length is fixed
For a given wave packet.
For a given source. Because the wave packet is produced by a particular source, correct? So for a given source, the coherence length and the coherence time are fixed. You don't have control over that. Now, of course, you can change the source to get a larger coherence length and longer coherence time. Okay, like that's why we always use lasers for interference experiments. Okay, but for a given source, the source determines the coherence length and the coherence time. So you don't have any control over the coherence length and coherence time.
Excuse me.
Yeah, Himanshu.
Yeah, whether any relation with lambda and coherence time or coherent length is there?
Of course. Yeah. Just coming to that. Yes, there is. Yeah, you can relate. So basically, can I clean this part? This one. Yeah. So C is nu lambda. So nu is C by lambda. So let me. I don't know how I'm not messing up with this thing. What do I? Yeah. So right. So C is nu lambda. So which means nu is C over lambda. So just the change in nu is related to the change in lambda given by this relation. So and then you just put this one here. So basically, so 1 over tau C. So if you want to relate tau C, then it's lambda square. So the sign can be ignored because this minus sign does not have any real physical significance. So just ignore that minus sign and this is what you have. Or if you want to relate this one to the coherence length, So does that answer your question, Himanshu?
Yeah, actually, I am Krishnan here, but yeah, it's
Oh,
fine.
I'm sorry. My apologies. Yeah, I thought this was.
Yeah, it's
Yeah,
no
go
issue.
ahead.
Thank you.
No, does that answer your question?
Yeah, I could able to find how it is related, but still I just need to think how physically whether the different lambdas and how the coherence may vary with respect to the wavelength what it can generate. But it's fine. At least I can see the relation how it is.
So
if the source is like say blue or red or something in a different colors, how the coherence time may vary with respect to that I was thinking. No issues, but with this I'll just try to relate with it.
Can you please repeat your question once again for me?
Suppose if the source is having say blue wavelength or a red, suppose. So whether the source coherence time or coherence length may vary or based on how it is designed only that matters.
No, the coherence length and coherence. See, the source can emit produce the field over a range of wavelengths. There is going to be a central wavelength around which there will be some spectral components.
Okay.
But you can see from this expression that if delta lambda is extremely small, then your coherence length is going to be much larger.
Okay.
So ideally, if delta lambda is 0, then your coherence length goes to infinity. So which means it's a perfectly harmonic wave. The ideal case.
Okay.
There's only one wavelength. It becomes monochromatic. Okay.
The spread. Okay.
Yeah. So the reason is now lasers have. So why is it that we can legitimately treat a laser as a monochromatic source? Because for a laser, the spread is extremely narrow. Okay. That's why it's a perfectly legitimate approximation to say that, okay, I have a laser at 810 nanometers, because the spread around 810 is going to be extremely small. And that's the reason why lasers have a much longer coherence length. I mean, of the order of the coherence length would be, say, 400 meters for a helium neon laser. So for almost close to half a kilometer, the laser maintains its coherence, right? Now, likewise, the same thing here. If delta lambda is extremely small, then the coherence time gets much larger. Okay. If delta lambda is 0, then coherence time becomes infinite. Again, that's the ideal harmonic wave, where you generate a wave and it remains harmonic forever over infinite distance for infinite duration of time, right? And this is the relation. This is the reason why a few minutes ago we argued that the temporal coherence is related to the finite bandwidth of the source. Okay. Now you see how the bandwidth of the pulse is related to the coherence time. Likewise, the bandwidth of the pulse is also related to the coherence length. Okay. When delta lambda is 0, then lambda has the wavelength is unique and the field is monochromatic. So otherwise, for any finite lambda, as long as delta lambda is it's not too large, it's small, we call the source to be quasi-monochromatic. You still have the central wavelength, which you call the mean wavelength. Some people call it the mean wavelength, but you have a spread around that wavelength.
Fundamental restriction to generate monochromatic waves. Like, is there any fundamental restriction like delta lambda cannot?
There is no. You mean so you can try to generate a laser which is and try to probably it's possible to generate a laser with an extremely narrow spread. So over there is, but still it won't be 0. The reason is any real optical source has a finite duration and has a finite bandwidth. So that one, you're right, that follows from the uncertainty relation or much beyond that Fourier relation. So delta t should be of the order of 1. So if we are going to make, if the beam is perfectly monochromatic, then which means it has to, the duration of the pulse has to be infinite. Okay. Likewise, delta z, delta k should also be of the order of 1. So delta z is a spread of the wave packet of the in real space. Delta k is a spread in the frequency space, which is the bandwidth of the pulse. So you can use lambda or wave vector, doesn't matter, right? Now, if the pulse does not spread in real space, if delta z is 0, then you know that the bandwidth is going to be infinite. Or if the bandwidth is 0, then in real space the pulse will occupy whole of real space. Okay, so in real world this never happens, and there's always a trade-off. So you try, so as an investigator, you decide which one you want to be large and which one you want to make it small. Like if for a particular problem, if you want a pulse that has a much longer duration, then you try to make that long at the cost of a narrow bandwidth. So the spectrum, it will only encompass a few spectral components in frequency. Okay. Likewise, if you want the pulse to really spread over a much longer distance in real space, then once again it comes at the cost of a narrow bandwidth, or vice versa. It's up to you. Okay, so now
excuse me.
Yeah, yes, please.
This coherence time and coherence length we are seeing for optical region, but if we see for microwave region, so in that case, as lambda is high, so coherence time will be high, or those parameters are not applicable in those regions?
No. The notion of coherence time and coherence length applied to the entire electromagnetic spectrum.
Okay.
So they are not confined to a particular region of the spectrum.
Okay.
Yeah, go ahead, please. Yeah.
But why that more focus is on optical region?
What's it? Why more?
Why this coherence? Because if we see classical communication using electromagnetic waves, microwave, for example, there these coherence time and coherence length are not of significant importance.
No, hold on. So right now the discussion on coherence is centered around the ability to observe interference. Okay, so when you try to transmit information over long distances, over there you're not worried about there is no interference, no diffraction, nothing. You just want to transmit the beam. So the only thing that you'll be concerned about is, as long as you can preserve the information or transmit the information from one field to another before it dies down, you're good. So over there, for transmitting information, I don't think the concept of coherence is of prime value.
No, I think perhaps what she's asking is, instead of optical wavelength, if you go to microwave range, will this, term, will not this term be meaningful, the coherence time, coherence length?
No, they'll still be meaningful because you can still do experiments with microwave photons in the quantum regime, or even classical microwave fields. You can do interference experiments with X-rays, whatever, ultraviolet, whatever. So the notion of coherence time and coherence length are relevant everywhere. It is just that, any throughout the electromagnetic spectrum. It is just that when we work out some examples or discuss some illustrations, we typically end up choosing examples from the optical part of the spectrum because that is something that we are used to.
When you have change, then the C will be. C is the speed of light.
The speed of light.
You have to change something there.
Yeah, if it's propagating to the medium, still these relations will hold good. It is just that over there, the C will be replaced by some V, which is the speed of the field in the medium. But this relation will still hold good. Very important.
Why they care about coherence time?
Yeah.
If I just have to transmit.
You just have to transmit. Over there, your only goal is you don't want to lose information. So which means you transmit, you have repeaters or whatever, you make sure that the information is transmitted from one field to another before it dies, before you lose the information. So over there, the notion of coherence is not of much significance. So can I clean this part of the board completely? So I want to just draw a table and write down some numerical values so that we just get a feel for how the coherence time and the coherence length change for various sources. So this is the source. So this bandwidth, this delta lambda, is also called line width in the literature. Okay, it's called line width because you have a central wavelength and then there's a width around that line. So it's called the line width for that reason. So bandwidth or line width will be used interchangeably in the literature. So if you happen to come across the word line width, it just means the spread. Okay, delta lambda, delta nu, or delta k, or delta omega. Doesn't matter what variable you choose to study, but if the spread around that central frequency or wavelength or wave vector, that spread is called the line width or the bandwidth. Okay, now so basically this is the formula for coherence length. Oh, sorry. So let us consider white light. At 550 nanometers, okay, and the spread, it's 300 nanometers. The spread is pretty large, and you will see that when we look at the value for a laser, for a helium neon laser. Now, the coherence length is 1 micrometer, and the coherence time look at this value. So L sub C is 1 micrometer. So
sorry, what are you telling me?
For a white light. For a white light.
For any white light, this is.
So for a white light, say at this particular wavelength, this particular spectrum of white light, 550 nanometer. Okay.
Coming from what source?
Take any source. It's a regular white light, which is a combination of all the wavelength spectral components.
Then how does it have 550 nanometer?
No, just pick a source at a particular wavelength and then see what is the spread around that thing.
The maximum
Maximum 550 is, so the intensity is maximum at this wavelength, and just consider the spread around that one. Okay, that's 300 nanometers. Okay, now the coherence length is 1 micrometer for this one. So which means if you want to perform Young's double slit experiment or any interference experiment, say you want to use Michelson's interferometer to observe interference with white light, the change in the path length, the difference in the path length should not be more than 1 micrometer. And that tells you why it's extremely hard to observe interference with white light. It's not that you cannot do it, but you'll have to really slog. You'll have to use some very good motor which can move. So you'll have to mount this mirror on a sophisticated piezo stage, which would move in steps of 0.05 micrometer or 0.1 micrometer, something like that, and then observe interference. Okay, and you can also look at the coherence time, extremely small. Now, this is mercury arc, okay, the mercury lamp. So it produces a field at 546 nanometers. So the spread is 1 nanometer. Now, if you calculate it, it's slightly better, 0.3 millimeter. Okay, and then 1 femtosecond is the coherence time. This is still better to observe interference. Now, let us take this krypton discharge lamp. Let us say it produces a field at 605 nanometers, and now it's 1.2 to the power times 10 power minus 3 nanometers. So still the line width is getting narrower and narrower. Okay, so if you do this one, 0.3 meter is the coherence length, and 1 nanosecond is the coherence time. Okay, still better. So the last one is, let us take helium neon laser. So this will take the cake. Generate a laser, a beam at 632. Look at the line width, 10 power minus 6 nanometer. That's why we are justified in treating a laser as a monochromatic source for all practical purposes. And you calculate the coherence length, 400 meters. Okay, you have a huge cushion as far as playing with delta L is concerned, playing with the path difference is concerned. And then the coherence time is of the order of microseconds. Okay, so this is why laser is the most sought after source for any kind of interference experiment. And that's precisely the reason why white light is not, it's the most unfriendly of all the sources for any kind of interference experiment. But the interesting thing to appreciate is, when Young performed his experiment, he didn't have the sophistication of using a laser. When Young performed his experiment in the 19th century, the double slit experiment, he didn't have all these sophisticated sources. So probably he had a white light or some other highly incoherent source, and nor did he have the kind of sophisticated piezo stage motors stands that we have today that can vary the path length in steps of few micrometers. So pretty much whatever he did, he had to do by hand. Okay, but despite all those limitations, he really performed an amazing experiment and really demonstrated the concept of interference.
White light.
Probably should have used white light or certainly one of these incoherent sources, or a sodium. I don't know whether he had I don't know whether in the 19th century people had sodium vapor lamp. I'm not sure, but certainly white light, or maybe the sunlight. Basically, yeah, white light. Basically, the sunlight. Historically, I don't remember on top of my head what source he used, but certainly it has to be either this one or, yeah.
Definitely, it cannot be laser.
Not laser, for sure. No laser. I don't think even he had this krypton discharge lamp in the 19th century. I don't. Yeah. But look at these numbers. That's why it's very inconvenient to perform interference experiments with this one. So that's why even you can't even give this as an assignment to students, like, okay, reproduce Young's experiment lab. It's going to be incredibly hard. So whatever experiment we performed in a typical optics lab is always with the laser. Okay, so the thing is this one. So yeah, I'll just use this part of the board. So the question is, so once again, the coherence length is always measured by using Michelson's interferometer. Okay, so once, just to repeat and reinforce this one. So what do? We have the source, yes, that produces a beam, and we have a beam splitter, and now both the beams will get reflected off of the two mirrors on the two arms of the interferometer. Okay, initially we keep the arm length equal. So now what we do is, let us say you displace this mirror M1 by a distance d. Okay, now if you do that, the change in the path length will be 2d, because it goes this way and once again it bounces back. Now what you want is, you want to observe interference. You want the change in the path length to be much less than L sub c. The smaller the path length, the difference in the path length is with respect to the coherence length, the better will be the quality of your interference fringes. The contrast will be much better. But the limiting value is, so this is the maximum. So when you reach this limit, you'll already realize that the contrast will be poorer, much poorer than what you have here. Okay, so beyond this, you will not be able to observe interference. So beyond this limit, if 2d is greater than L sub c, okay, if the path difference is larger than the coherence length, all you will see is just some uniform or fuzzy distribution of intensity on the screen. You will not be able to observe the fringes. So that's how the path length is determined experimentally. Once you know L sub c, tau sub c is 0. I mean, it's trivial. So just divide this by the speed of light. That gives you the coherence time. So it's, in a lab, it's easier to measure. It's more natural and direct to measure the coherence length. And then from that, you infer the coherence time. Okay, so this is as far as the temporal coherence was concerned. Now the question is, can we investigate spatial coherence? Because spatial coherence has to do with the finite dimension of the source. Because any source is not a point source in the lab. In real world, you have an extended source. Okay, so which means each point on the source will not be, so you will not have coherence between various points in the source. So each emitter will emit randomly, and the field produced by one emitter will not be coherent with the field generated by the other emitter in the source. So the question is, when you have an extended source, how do you quantify, or how do you appreciate the concept of coherence? So that's where the spatial coherence comes into account. It simply comes from the finite size of the source. So is there a simple experiment, or a simple setup that we can use to get a feel for the concept of spatial coherence. In other words, can we come up with some kind of a limit on how large the source can be, the extended source can be, to observe interference? Because you cannot arbitrarily make the source larger and larger and still hope to observe interference on the screen. Okay, so there's going to be some limit on how big the source can be. So can we do that? So yes, it can be done. And what we will do is we'll once again use the setup for Young's double slit experiment to come up with an estimate on how large the source can be. No, that's so line width has to do with temporal coherence. Yeah. So as far as the random distribution of phase, that is common to both spatial and temporal coherence. But when we discussed temporal coherence, like coming up with the notion of line width, with the coherence length, so on and so forth, we didn't explicitly talk about how large the source is. So here we just want to look at Young's double slit experiment and come up with an estimate on how large the source can be. It's like you don't have a, so typically in the ideal case, we just treat the source as a point object, right? But let us say that you treat the source as an external object of length L. Now, can we estimate how long this L can be, and so that you still observe interference on the screen? Is there some kind of estimate beyond which, if you make the source longer than a certain limit, then can we conclude that okay, we won't be able to observe interference anymore? So basically, what I'm saying is, in general, so you have an extended source. Each point is going to produce its own field on the source, and in general, the fields will not be correlated with each other. The fields produced by each point will not be correlated forever, in general, because the source is an extended object. Okay, and that's the kind of source you always have in the lab. So the question,
we will not fall under the coherence length, basically.
Yes. So this L is different from the coherence length. So we are using L because we basically run out of letters. So, and Greek letters are always used for certain specific quantities like angles, so on and so forth, phase. So again, we are stuck with English letters. Yeah, or maybe we should use Greek Russian letters or whatever. Indian letters. So can I just clean this part of the board? So everyone, I can clean this part of the board, right? Because I need it. Wait. Okay. So let us consider a source that's of length L. Okay, we are just going to consider this dimension. Okay, we are not going to treat it as a three-dimensional object. Okay, now there are 2 points at the 2 edges. Label them, one of them as S, the other one as S prime. Okay. So these are the slits, S1 and S2. This is the screen. This is point O. So let me just call this distance A1, A2, and A1 plus A2 is the total distance from the source to the plane where you have the slits is A. Okay, and we don't worry about this distance. One second. No, okay, I'm sorry. No, I won't. Let me call this L. Sorry, I have a reason. So this point S on the source is equidistant from S1 and S2. Okay, this is what I want to. This is how I want my setup to be. Okay, now this point S is equidistant from the slit S1 and S2. Okay, and now I have another point S prime that's part of this extended source, and the distance between S and S prime is L. Okay, now of course, so in general the field emitted by S prime will not have a definite phase relationship with the field produced by S. They may, in general, they don't have to, they will not, they may not have. Okay, if at all they have, it's a coincidence. Okay, so the interference pattern observed on this, now if you consider both these points S and S prime on the extended source, the interference pattern observed on the screen, this is the screen, will naturally be the superposition of the interference pattern due to S and S prime. Correct? That's something that is intuitively clear to us. Okay, that's what we expect, right? Now, if you only have one point S, in other words, if L is 0, which means S and S prime become one and the same, it's a point source. Then that is the case of the standard Young's double slit experiment that we have seen in the high school, right? Now, if you slowly start changing L, in other words, you start moving the point S prime and you make the source more and more extended, intuitively you would expect the interference fringes to become poorer and poorer as you keep increasing L, correct? Because in general the field produced by S and S prime do not share, they don't have to share any phase coherence. Okay, so which means as you keep increasing L arbitrarily, the two fields will become more and more incoherent. So which means the superposition of interference fringes will not result in a combined interference fringe of high contrast. Okay, that's what you would expect intuitively, right? So what I mean is, the source, imagine the source is as one composite entity like this duster. Okay, now this L is what we are considering here. Okay, so this is your S and this is your S prime, correct? Now if you just start with the point source, then if you just forget this length, then we just have one point here, S. Okay, and over there we know how we observe interference, because we just have one source that produces a wavefront, it passes through both the slits, we know the analysis. Now you slowly start changing, increasing L, so which means S prime is S prime no longer coincides with S, so you start moving S prime away from S, so which means your source becomes more and more extended, right? So which means S will produce its own field, a wavefront, S prime will produce its own wavefront. Okay, and both will pass through the slits S1 and S2 and they will interfere. So the question is, so whatever you observe on the screen will be a superposition of the interference due to S and S prime, correct? So what we want ideally is, if you now want to treat the source as one composite entity, what we want is, we still want high quality interference fringes. So which means even though there are two points S and S prime separated by a distance L, what we hope to achieve is that you will still be able to distinctly see the bright and the dark fringes. In other words, you don't want the dark fringe from S prime to overlap with the bright fringe from S. You don't want that. Likewise, you don't want the bright fringe from S prime to overlap with the dark fringe from S, because if that happens, what will happen is that the contrast vanishes. And of course, we are not saying that there won't be any distribution of light on the screen. It is just that it will be some uniform or a fuzzy distribution of light without the contrast. Because the moment the dark fringe overlaps with the bright fringe, or vice versa, the distribution becomes uniform. You will just see capture some intensity on the screen, but that won't be the interference pattern. But our goal is to still observe the interference pattern on the screen with an extended source. So can we deduce some condition, or can we come up with some limit on L, or how long or how large or how small should L be, so that we can still observe interference for an extended source when S and S prime are separated by some distance. Okay, that's what we are trying to investigate here. Any question? So this is the goal here. Okay. So when will the interference disappear? The interference will disappear when the minima from S prime coincides with the maxima from S, correct? So which means it's when S prime S2 minus S prime SS2, that's when the interference vanishes. Because that's so you observe constructive interference for integral multiples of the wavelength and destructive for half integral multiples of wavelength. Okay, so in this condition, the interference pattern produced by S will fall on the maximum of the interference pattern produced by S prime. Okay, which means the contrast vanishes. Okay, so now the question is, what is S prime S2? I'm sorry, S prime S2 and S prime S1. Sorry. So S prime S2 is simply going to be, this is S prime and this is S2. This length is A, correct? So, and what I think I believe the slits are separated by a distance D. Yeah. Yeah. Just because you can just pick any 2 points and do the analysis. In principle, you can, so that will hold, the analysis will still hold for any pair of points. Okay, we are just picking 2 specific points for the analysis, and that condition will hold good for the entire source.
Bright interference fringes should coincide with the dark interference.
Yeah. Yeah, sure. Because what you want is you come up with the condition for the destructive interference for this one. Okay, and that should coincide with the maxima of the other one. Yeah. Oh. So once we do this one, yeah, S prime. Yeah. So this S prime S2 is simply going to be this is what it is, because S prime S2. So basically, this is going to be L plus D over 2. So this is L, and this one is the separation between the slits is D. So this is just going to be D over 2, and this is L. So this is a right angle triangle. So this S prime S2 is simply going to be a square plus d over 2 plus L the whole square and square root of that one. Okay. Now, of course, this A is much larger than D and L. This distance is obviously much larger than the length of the source as well as the separation between the slits. So basically, we just use a binomial expansion. We do a binomial expansion and just retain the first term, the first order. So if you do that, you will get this is what you will get. Now, the same thing we can write for S prime S1, which is this one. Okay, and that is going to be exactly identical, except of course I should be careful here. It's not exact, it's just approximate because we are truncating the expansion. Okay, now if you take the difference, you will just be left with LD over A, because only the cross term will survive when you take the difference. Okay, and that should equal half wavelength, so that the maxima from one point coincides with the minima from the other and vice versa. Okay, or which means the moment the length of the source reaches this, okay, you will no longer observe interference due to this extended source.
That's also depending on the D.
Yeah, of course, it depends on a slit separation. But of course, for a given, it means that you fix the separation between the slits. Okay, once you build your setup, you fix the separation between your slits. Okay, and you also fix the location of the source such that you don't play with this distance. Okay, then the question is, how much can you play with L? How extended can you make the source?
So this A, just to summarize, A is the distance between the source and
the slits, and the plane containing the two slits. Okay.
So it is A1 plus A2.
A1 plus A2, yeah. Okay. That's what it is. Now, of course, if this difference, instead of being lambda over 2, if it is lambda, then which means that the maxima from S prime will coincide with the maxima from S, correct? Because that's the condition for constructive interference. Ideally, that's what you want. So you get the best contrast when the maxima from one coincides with the maxima from the other point. Likewise, the minima coincides with the minima from the other point, correct? So which means if L is much less than lambda A over D, because this 2 goes away, because for constructive interference that half does not appear, correct? Now this is when your interference, you'll observe the best interference, because you're making the separation much smaller than this quantity. Okay, so this just gives a good estimate. Of course, this is something that you would have also seen. No, this L is not related. No, D is not. No, this D is just the separation between the slits. So you can. Which one? Say that again. Here. Yeah. So the thing is this. Yeah, so if you make the separation between the slits larger and larger, then your source cannot be more extended. You see, if D increases, then L goes down, correct? So which means if you want to make the slits much wider apart, then your source has to resemble more and more of a point source. In other words, if your source happens to be reasonably larger, if it is quite extended, and if you still want to observe interference, then it's very important that you make the two slits as close to each other as possible.
Somehow the spatial distance between them should be small enough to observe interference at the very first.
No. So ideally, to observe interference, the field you should have both spatial and temporal coherence. So both these kinds of coherence do exist always in an optical field. But it's just that we are investigating them separately because they're slightly different concepts. Like one related to the bandwidth, finite bandwidth of the source of the field, the finite line width, and the other is related to the finite size of the source that produces the field. Okay, so this is what it is. So today we just resorted to some simple elementary analysis to get a feel for what coherence means. But this analysis certainly is not sufficient, because the reason being that the fields produced by the source, by each emitter in the source, are statistically independent. So which means naturally, in order to carry out a rigorous analysis, we will have to invoke concepts from stochastic processes so that we are able to define the correlation functions legitimately. So that's what we will do next time. So we will review some of the basic ideas from stochastic processes that are of relevance to study optical coherence. So we are not going. Statistical optics. So basically, the notion of a white sense stationary process, the autocorrelation functions, the cross correlation functions, and then we will also introduce the concept of analytic signal. So any optical field can be represented as a complex analytic signal. That is just to simplify the calculation. In reality, the optical fields are real functions. Unlike quantum mechanics, where the complex quantities naturally enter, you don't need complex quantities to study classical optics. Everything can be worked out by simply treating the fields as real quantities. It is just that the mathematical calculation becomes simpler when we treat them as complex quantities. So we will just introduce a notion of complex analytic signal. Of course, we will not be going into the mathematical aspects from complex analysis. We'll just introduce the ideas that are relevant for our investigation. Okay, and then we will start discussing interference, temporal and spatial coherence in terms of these correlation functions. Okay, and then move on from there, and then slowly we'll find our way into quantum optics as how these ideas get carried over to the quantum regime. Of course, the concept of coherence in quantum optics is even much wider. So here, the coherence was just related to spatial and the temporal aspects. So basically, having a predictable amplitude and phase between different points and at different points in space and at different instants of time in an optical field. But in quantum optics, the notion of coherence also arises due to path indistinguishability. So if you cannot observe the path of a photon, you will observe interference. So the concept of coherence is even much deeper and richer in quantum optics. Okay, so we will discuss some of these ideas later, but the next few lectures will simply involve the study of coherence within the realm of classical optics. So next time we will discuss some ideas on statistical optics. At least appreciate the notion of white sense stationary process, the notion of ergodicity, then the concept of analytic signal, and then try to relook at some of these concepts in the framework of correlation functions, and then try to look at how spatial coherence and temporal coherence are investigated in terms of these correlation functions. So that's so we basically will be following the approach that Emil Wolf developed. So one good source to appreciate some of these ideas is this beautiful book by Emil Wolf. So this is the last book he wrote in his life. That's Introduction to the Theory of Coherence and Polarization of Light. But a more exhaustive and encyclopedic version is available in the thick book that he wrote with Mandel, Optical Coherence and Quantum Optics. But that's way too advanced. Okay, and Wolf has given a lot of information, but this is a more elementary approach where he has only discussed the essential ideas. So this is one good place to look at to appreciate some of the rudimentary aspects of optical coherence. Okay, so this Friday we won't meet because we have a group meeting. So the next lecture will be on Tuesday, a week from today at 2:15. But again, from next week onwards, we'll meet on Tuesdays and Fridays from 2:15 to 3:45 or whatever. Okay. So
Thank you.
So any question?
I mean, did you calculate that for like fringe in the center of the center of the...
So here, of course, forget S prime for a minute. Okay, if you just consider S, you know that the center will have a maxima. Okay, so the spirit was you ignore S prime and treat this as a point source. Okay, now that's the standard Young's double slit experiment that we are used to, where the source is symmetrically placed from the two slits, which means the center will have a maxima.
Yeah.
Okay, and then you introduce this point S prime such that S prime and S are separated by a distance L. So so the whole thing is an extended source. Now then the goal is you don't want, of course, this is the limit where the minima from S prime will coincide with the maxima at O, and likewise at all the other points. Okay, but as long as this condition is satisfied, okay, then the maxima will coincide with the maxima, the minima will coincide with the minima, and you will still observe interference for this extended source. So which means the field will be spatially coherent. The source has a finite size, still you will observe interference. Even
any integer multiple of lambda.
Yeah, sure. But then you, when you do the analysis, you just take the lowest order, because the goal is to estimate this one. How small or how large can something? Yeah, please.
The concept of coherence can be associated to single photons, right?
Yes, of course.
So for a source that emits photons continuously, then the coherence length can also fluctuate.
So no, when you say when you say photons emit continuously like a laser. For a laser, of course, the notion of coherence length is well defined, like because the moment. No. For a weak source. Oh, so if you consider a single photon, just one photon, then and then you want to still observe interference, then the concept of coherence over there will arise out of erasing the path information, basically from path indistinguishability. So by not knowing which path the photon, because photons are indestructible. So you put a photon in front of a beam splitter, it can either get transmitted or reflected. It cannot split itself into two. So as long as you don't know the path it takes, you will observe interference. So or let us say, if you, I think a simple, I think, can I just take 2 more minutes? So you have a source, okay? Let us say it produces, you generate light that's polarized at 45 degrees. Okay. You put a polarizing beam splitter. So this, let us say this is H, this is V. This is a regular beam splitter, non-polarizing beam splitter. So which means this will not split the beam depending on the polarization of the photon. Okay, it's a regular beam splitter. This is the screen. Now, if this polarizer turns out to be a standard polarizer that's going to block either horizontal or vertical, then there won't be any interference, because you have H here, you have V here, so this is just going to admit one of them depending on which way this polarizer is oriented. Okay. Instead, if I once again put a polarizer that is oriented at 45 degrees, then this will allow both H and V, right? Because both H can pass through this 45-degree polarizer and V can pass. So which means the moment what comes on a detector of the screen, once you observe the photon here, you don't know its source. You don't know whether the photon was from this arm or that arm. Okay, so basically you have erased the path information. So if you put a 45-degree polarizer here, you will observe interference. But instead of a 45-degree polarizer, if it is just going to be a polarizer that is either oriented along the horizontal or the vertical axis, then there won't be any interference here.
What if it is at some other angle? At a 45.
No, but then the question is, it depends. So you can still observe interference, but the contrast will change, because you will get the best contrast because you have completely erased the path information. But if the erasure of path information is not complete, it doesn't mean the interference vanishes. It's just that the contrast will be reduced. And when there is a perfect, complete revelation of the path information, the interference vanishes. So this is how the concept of coherence and interference manifest at the single photon level.
I mean, if we have a source and it's not just emitting one photon, it is emitting multiple photons at a time, right? So and the coherence length for each of them, because it's because of randomness that this.
If you're going to treat this as a laser where it just emits many photons and intense beam, then you can simply reproduce the classical analysis.
If we have a coherence length, do we have fluctuation around it?
No. The coherence length is pretty much once you determine, there is no fluctuation around the coherence length. It's just you determine the coherence length, and that's what it is for that particular source. Of course, when you say determine to the best of your ability in terms of the precision of your experiment. To that extent, yeah.
From a color, like some form of light or electronic spectrum somewhere. The point is, even if you are injecting photon, your delta lambda is fixed.
That is true.
So that means coherence even.
No, but for single photons, do you have a concept of coherence?
No, single photon. No, the whole thing is for a single photon. The notion of interference itself comes from the absence of which way information.
This again boils down to this notion of wave function for a single photon.
Yeah.
We don't have photon wave function.
No, we don't have a photon wave function.
So then how will you talk about the coherence length then?
Yes, so no, we don't have a notion of wave function for a photon. The only thing for a photon that we can write is, if you know that you have a single photon and you want to describe its state, then in the multimode, what you do is all this tells you is that you have a single photon pulse with this particular spectrum. So what this f of omega tells you is that if you were to slice the spectrum into several bins, each bin will tell you the probability of finding the photon in that particular bin, because a single photon can be anywhere in the pulse. Okay, and so basically mod f of omega square gives you the probability of detecting a photon at a particular frequency bin. But from this, we cannot just define L sub c and tau sub c for a single photon. Okay, so this, of course, this also has a spread around the central frequency, but this spread is not, we just can't relate the spread to delta, yeah, this tau sub c and L sub c that we discussed in the classical regime. So here coherence is really due to, for a pure single photon, coherence is really due to the absence of which way information.